Hi guys, Mrs. Warner here, ready to do some angle of elevation and angle of depression. So if you're in your note packet, you're on lesson 6.3. It says angle of elevation and angle of depression at the top. Isn't that crazy? So first of all, what are these elevation and depression angles that we're talking about? Well, they have to do with trig, and you'll see why in a few moments. So first of all, there's a difference between the two. Angle of elevation is, say you're here, you're an observer, and the angle of elevation and depression is made with the horizontal line of sight. So you're horizontal here and your line of sight as if you were like looking up at an object. So say you look up in the sky and all of a sudden a bird flies by, or like Superman or something else, which would be super exciting. So you look up at that object, that angle that is made with the horizontal, which is generally parallel with the Earth's surface, is your angle of elevation. So this angle in here with your line of sight to the object is your angle of elevation. Now, so you were standing on a cliff and you were looking like down in the ocean and you saw a shark down there. So now you're looking down at your object. And the angle that's out here is your angle of depression in there. Now, the cool thing is, if you were standing at the bottom of the stairs and someone was at the top of the stairs and you guys were looking at each other, if you drew in your horizontals and then looked at your line of sight, those horizontals are going to be parallel to each other. And you can actually see that those angles elevation and angle of depression are actually equivalent to each other because they're just alternate interior angles. Because we know that if two parallel lines are cut by a transversal, then the alternate interior angles are equal in measure. So really, angle of elevation is the same as angle of depression. So let's try a problem. Let's look at example 1. It says label the angle of elevation from the observer in the boat to the top of the lighthouse. So if I go to my picture, I see my boat here, and he's going to be looking up at the lighthouse. Now it says that angle of elevation is 43 degrees. If the lighthouse is 175 feet tall, so I'm going to put that on here, how far is the observer from the base of the lighthouse? So that's going to be my x. I'm looking for that distance that the boat would have to be to the base of the lighthouse, or I'm looking for that horizontal distance. Now, if you label your pieces in your triangle, the 175 is opposite your reference angle, and the x is adjacent. So my function that I'm going to use in this case is going to be a tangent. So I'm going to use tan of 43 is going to equal 175 over x, just like we've done in previous problems, and I'm sure we all did our delta math. So if I put this over 1, now I can cross multiply it. So the tan of 43 x equals 175. And when the x is on the bottom of the fraction and we have cross multiplied, it's like saying 5x equals 175. So now I need to divide both sides by that function. That's the tan of 43. So I'm going to take 175 divided by the tan of 43 in my calculator. And of course, my calculator is in degree mode, everyone. And I end up with 187.664 and a bunch of other decimals. This says round my answer to the nearest foot because I'm going to read the problem carefully because I know we all do that. And its x is approximately 188 feet because I had to round it to the nearest foot. That was super fun. So angle of elevation, we were looking up to the top of the lighthouse, and we were able to find our distance that the boat was to the base of the lighthouse. Let's look at our next example here. We have a label the angle of depression. Oh boy. So now remember, the angle of depression is actually with your line of sight. So that's actually out here. Angle of depression will never be put at the top of the triangle on that spot there, unless there's some weird situation where they tell you to put the angle there. Angle of depression doesn't mean it's at the top of the triangle. Because remember, in our example up above here, we know depression and elevation are actually the same angle, so they're going to end up in the same spot. It's telling us this angle of depression is 36 degrees. So I'm going to flop that down here because they're alternate interior. It says the horizontal distance from the tree to a spot directly below the air balloon is 465 feet. So along our horizontal here is 465 feet. Find the height of the hot air balloon. So I need to find how tall the hot air balloon is off the ground, or its vertical distance. If I label my pieces again according to my reference angle, this is my opposite and this is my adjacent. So once again, I'm going to use my tangent. So the tan of 36 is equal to x over 465. This time our x is on the top of our fraction. I'm going to put this tangent of 36 over 1, and I'm going to cross multiply. So x is equal to 465 times the tan of 36. When I punch that in my calculator, which is in degree mode, I get 337.8422 and so on. And I'm going to round that. I'm going to go back to my question and read, because that's a crazy concept. It says to the nearest tenth of a foot, so 337.8 feet, because the 4 rounds that to 0.8. That was super fun, people. So what you're going to do now is you're going to try these 4 examples here. Example 1, 2, 3, and 4. 2 and 4 are a little tricky. Read this carefully. Scott is 1.5 meters above the ground on example 2. So that means his line of sight has to come from his eyeball up to the bird. And this distance here is 1.5. So when you're using your right triangle, it's actually up here in the sky. Then when you get done with your problem, you're going to add in that 1.5. Similar to that problem down here in example 4, we have the rooftop is 16 meters from the ground, and then this is 16. Why won't it let me write? Oh boy, that came out messy. And then John's eye level is about 1.8. So really, if we're looking down to here, we have this 16 and 1.8. So it's really like 17.8. Those are my hints for you. Okay, get those questions done in your Go Formative before moving on to lesson 6.4. Okay. So let's move on to lesson 6.4 down here. So in lesson 6.4, we're just simply plugging in decimals into our calculator and calculating some things with our functions. So you're going to type in sine of 50, cosine of 40, get their decimals. Sine of 20, cosine of 70, get their decimals. Same thing for all of these. Now, when you're getting your decimals, you should observe something about problems 1 through 5. So it says down here, what do you notice about the decimal answers for questions 1 through 5? Well, on 1 through 5, their decimals are the same. So all of your decimals should come out to be the same number. So for example, on the sine of 30, it's 0.5, and the cosine of 60 is 0.5. The next question asks, what do you notice about the sum of the angle measures for 1 through 5? Well, if I took 50 and 40 and added them together, they add to 90. 20 and 70 add to 90. Sure enough, 30, 60, 80, 10, 27, 63, they sum to 90 degrees. They're complements of each other. But what do you notice about the sum of the two measures for angle 6? Oh shoot, if I added 77 and 33, those add up to 110. They don't sum to 90, and if you noticed, their decimals are different. So if the sine of A was equal to the cosine of B and A was 53, how could I figure out what B was? Well, according to above, if they were equivalent decimals for sine and cosine, their angle measures would have to sum to 90. So if I know that out of the 90, I have 53 degrees, I would do 90 minus 53, and I think I end up with 37. So that angle measure would have to be 37 degrees because technically they are complementary. Oh boy, I ran right off the page. They're complementary. Look how good I'm music Kimmy. I'm pretty awful at it. So it says if two angles are complementary, then they have a cofunction relationship between sine and cosine. So if the two angles sum to 90 degrees, they have this co-function relationship between sine and cosine. And we talked about that before when we saw that the sine fraction and the cosine fraction, depending on the two different acute angles, were just like the opposites of each other. So technically, if you know the sine, oh boy, of A, then it's equal to the cosine of 90 minus A. Or the sine of A is equal to the cosine of B, but you know those two angles have to add to 90 together. So you can think of B in terms of 90 minus what A was. So let's look at some examples. We know that the sine of X equals the cosine of 63. And I want to solve for X. Well, I can set up a simple, fun algebraic equation where X plus 63 is going to sum to 90. If I move 63 to the other side, I think I end up with 27 for my answer. And sure enough, that value is 27. So same idea here. If I know that one of the angles is 34 and I'm trying to find the other one, they have to sum to 90. Super important to write this algebraic equation. If you just write the answer down on a test or quiz or say it was a Regents, you would not get full credit because you have to show that their sum is equal to 90 degrees. So now X here is going to equal 56. So even though you could do those numbers in your head, you still have to write them down. So now let's look at our next one here. We have 2x plus 1, or 2x minus 1, plus 11 this time is going to equal 90, or 2x is going to plus 10 equals 90, or if I move that 10 over, 2x equals 80, or x is 40 for that value. Super fun. Next one, x plus 5 plus 4x plus 10 equals 90. And you guys can solve it from here. I know and have faith that you can do all the rest of these problems here and enter your answers in your Go Formative. You're also going to take a fun, super fun picture of both sides of your notes and upload that into the classwork tab with the Go Formative assignment for these 2 pages. Happy calculating. You can do it, people. I'll miss you guys, and I will see you on, I don't know, Friday? I'll see you Friday. Bye, everyone. Get outside.